So this video is going to go over day 2 in terms of the crystal violet, what you're going to be doing there, and then the subsequent calculations involved with this lab. So on day 2 is where you're going to actually take the crystal violet stock and you're going to react it with the sodium hydroxide into 100 ml volumetric flasks. So you're going to set up one reaction where you have 10 mils of stock with 5 mils of hydroxide, and then dilute it up to 100. You're going to take 10 mils, dilute it up to 100 mils. So this gives you practice with using pipettes and flask, and you're going to monitor each one of these reactions for a total of 20 minutes. Do not think that once you put the sodium hydroxide, yes, the crystal violet will start to dissipate or go away. That is not important that you get a reading right away, because we're just tracking it for 20 minutes and it takes more than 20 minutes for it to completely go away. So don't feel rushed that you have to, get that sample read right away. And you'll be using the same spectrophotometer you used on day 1. The only tricky part to this is every time you take a reading, you're going to take a reading every minute. You have to transfer the solution back to the original solution, because otherwise you're going to be heating up that sample, and we know that if we heat up any kind of sample, the rate will change. So that's going to be the most tedious part of this, is the fact that you have to keep going back and doing that. So you're going to do 2 separate reactions, one with 5 mils, one with 10 mils. And so what you're going to do is create a data table. For every minute, you're going to read it for a total of 20 minutes. You're going to write down the absorbances. So I would suggest that you create some kind of spreadsheet for this. And then from that absorbance, okay, you are going to essentially take the slope that you found from day 1 from your calibration curve, divide that into the absorbance, and that's going to give you the calculation for the dye. That's going to give you the concentration of the dye, excuse me. Then what you're going to see in my lab, I have you do multiply by 10 to the 6th, just because the size of the number, but you don't have to do that. And then you need to take the natural log of the concentration, because you will be graphing that. So again, for the dye calculation, you're going to take the absorbance you get off the spectrophotometer and divide it by the slope to get the concentration, and then you're going to do a series of calculations. So what your goal is to determine how does OH affect the rate of the reaction. So if we write a general rate law, we have rate is equal to K times the concentration of the dye to the power of M, and then a concentration of hydroxide to the power of N. So what we're trying to do is we did 2 separate experiments, experiment 1 and 2, and we're trying to see how did that affect the rate of the reaction. So we have to graph this. So there's going to be 3 graphs that you're going to have to make for this data set, and add to it. So one is going to be the concentration of crystal violet versus time. One is going to be the natural log of crystal violet versus time, and then 1 over crystal violet versus time. So this, of course, is going to tell you if it's 0, first, or second order. So the one that is most linear is going to be the one that is going to be the order of the OH. So what is N going to be? So depending upon your data, again, you might have a straight line for 2 things, or maybe it looks very straight. You have to compare their R values to see how close they are to really hitting that line or not. Whichever one is most linear, you are then going to graph both sets of data. So reaction 1 and reaction 2 are going to be on the same graph, meaning the one with 5 mils versus 10 mils, and I might be proportionally off there, both sets of data is going to go on one of the graphs. Now again, you're going to have to look at all of your data, one set of it. So take all of the 5 mils and graph them, and then see which one is the most linear, and then put the 10 mil on that same graph. From that, you are then going to be able to figure out from the slopes of those lines. So you're going to have a slope 1 and a slope 2. That's essentially going to be the rate of your reaction, because rate is going to be molarity per time, and our time here is going to be in minutes. So we could do rate as being molarity per minute, okay? So if I take, come on, focus camera, you could focus. I know that in one of my reactions, I have twice the amount of OH than I do the other. So I have 10 mils in this reaction, and I only have 5 mils in this reaction. So if I were to divide those two out, I would essentially get my value for N, because if I know my slopes, if I divide my two slopes, I could then figure out, well, one is twice that amount. So what does N have to be? So what you will have to do is figure out N, okay? And it's going to be a decimal, okay? So is it close to 0, 1, or 2? But it's going to be approximate. That's why I say a decimal. And then what is your K? So go back to your rate law, okay, and plug in concentration of dye and its power of, it's going to be a first order reaction, and then your OH, whatever N happens to be, and then take one of your slopes and then find your K. Okay, so that's what you're going to be doing calculation wise. And then to finish it all up, explain two errors and how it would affect your data. So how would you see that the graph would look differently if you had a particular error associated with the spectrophotometer, with how you made up the dilution, so on and so forth. So that's going to be the background to the lab.